Find somewhere comfortable tonight. You don't need to sit up straight or keep your eyes open. You don't need to hold on to anything that was said today or anything that needs to be said tomorrow. Whatever you carried through the hours since this morning, you can set it down now, gently, the way you'd set down something heavy you'd been holding for a long time without realizing it. If you're in bed, let the weight of you sink a little deeper into the mattress. If your shoulders are somewhere up near your ears, let them fall. The ceiling above you isn't going anywhere. The dark is patient. Tonight we're going to wander somewhere vast and ancient together. We're going to follow a story that began long before there were eyes to see it, long before there was a word for beautiful, long before there was anyone to stand outside on a quiet night and look up and wonder. We're going to talk about the moon. Not the moon of calendars and tides and romantic evenings, though all of that is woven in. We're going to talk about where it came from, how something so gentle and steady and familiar was once the product of something almost beyond imagining. You don't need to follow closely. You don't need to remember any of this. We're in no hurry here. Before there was a moon, the nights on Earth would have been genuinely, profoundly dark. Not the dark of a power cut, or a cloudy evening, or a country road without streetlights, something deeper than all of those. A darkness with real weight to it. The stars would have been extraordinary, blazing and thick across the sky, the way they still are in the most remote places on Earth. But the in-between spaces, the stretches of sky between stars, would have been absolute, the kind of dark that our ancient ancestors, if they existed then, would not have been able to see their own hands in. There is something interesting in imagining that. A world with no moon. The tides would have been a fraction of what they are now, pulled only by the distant sun. The nights would have offered no soft navigation, no quiet companion rising in the east, no silver path across the water. The earth itself would have wobbled differently on its axis, tilting and lurching over long stretches of time in ways that might have made the climate swing between extremes we can barely picture. The moon, in other words, is not just beautiful. It is stabilizing. It has been holding something steady for a very long time. And that steadiness, that quiet reliability, began in fire. It is a thought worth sitting with before we follow it all the way back to the beginning. The thing that hangs in your sky tonight. The thing that has been called Luna and Selene and Tsukuyomi and Mamaquilla and 1,000 other names in 1,000 other languages. The thing that pulls the oceans and lights the path home and has watched over every sleeping creature that has ever lived on this planet. It was born in a collision so immense that the word violent doesn't quite reach it. And yet here it is, quiet, patient, still. To understand how the moon was made, we have to go back to a time when the solar system itself was very young. Not young in the way a child is young, or even young in the way a mountain range is young. Young in the way that makes 4.5 billion years feel like a recent Tuesday. The solar system formed from a vast, slowly rotating cloud of gas and dust. Over an enormously long period of time, gravity began doing what gravity does, pulling things together. The center of that cloud grew denser and hotter and eventually ignited into our sun. Around it, the remaining material began to swirl and clump and collide, gradually over millions of years, assembling itself into the planets we know. This process is called accretion. It is not fast. It is not graceful. It is more like a slow accumulation of small collisions, debris gathering into pebbles, pebbles gathering into boulders, boulders gathering into something that begins to feel like a world. The early solar system was extraordinarily crowded with these objects. Planetesimals, they are called, a word that sounds almost like something from a poem. Tiny planets. Protoplanets. Wandering bodies of rock and ice and metal that had not yet found their final homes. The early Earth was one of these accumulating worlds. It was not yet the Earth we know. It was hotter, denser, more geologically restless. It had no oceans yet, no atmosphere worth speaking of, no life of any kind. It was a molten world, or something close to it, a ball of rock still radiating the heat of its own violent assembly. And somewhere in that same crowded region of space, another body was assembling itself. Roughly the size of the planet Mars, which is about half the diameter of present-day Earth, it was following its own orbital path around the young sun. Scientists have given it a name now, though it had no name then, and there was nothing alive to give it one. They call it Theia. The name is borrowed from Greek mythology. Theia was a Titan, one of the ancient divine beings who preceded the Olympian gods. In the old stories, she was the mother of Selene, the goddess of the moon. It is a beautiful choice of name when you think about it, a way of honoring the fact that what was about to happen would produce something that generations of human beings would eventually look up at and call divine. Theia was not on a stable orbit. Over millions of years, the gravitational interactions between the growing planets in the inner solar system were nudging it, slowly, inexorably, toward a path that intersected with the early Earth. This was not a sudden thing. It was not a moment of decision. It was simply what gravity does, patient and unhurried and absolute. And then, somewhere between 60 and 175 million years after the solar system first formed, Theia and the early Earth met. The word collision does not do it justice. Theia did not crash into the Earth the way a stone crashes into a pond. This was not a glancing blow, not a scrape, not a near miss. The current scientific understanding suggests it was an oblique impact, not perfectly head-on, but not a gentle graze either. Something in between, and the scale of it was such that both worlds were, effectively, destroyed in the process, and something new was made from what remained. In the moments of impact, the temperature at the collision point would have been extraordinary. Rock does not simply melt in those conditions. It vaporizes. It becomes gas. A vast plume of superheated material, the shattered mantles of both Theia and the proto-Earth, mixed together in the chaos, was flung outward into space. Some of it escaped entirely. Most of it did not. Most of it was captured by the gravity of the larger body at the center of the collision, which was what was left of the proto-Earth, now reassembling itself from the wreckage. What remained in orbit around that reassembling Earth was an enormous disk of debris. Vaporized rock cooling into droplets, chunks of solid material tumbling through the dark. A vast, slowly rotating cloud of everything that had been the outer layers of two worlds. And within that disk, the same process that built the planets began again, but much faster. Because the material was already there, already in orbit, already moving in roughly the same direction. It is thought that the moon assembled itself from this disk within a few thousand years. In geological terms, that is almost instantaneous. A few thousand years is nothing. It is the time between the first human cities and now, in the context of a solar system that had already been forming for millions of years. The moon essentially appeared overnight. What emerged from that disk was a world about a quarter of the size of Earth, still molten, still intensely hot, a magma ocean hundreds of miles deep, covering the entire surface. The young moon glowed. If there had been eyes to see it, and there were none, not yet, not for billions of years, it would have been a sight of extraordinary, ancient intensity. A second sun, low and vast and red-orange in the sky of a planet that was itself still healing from the violence of its own creation. Over time, the moon's surface began to cool. The magma ocean slowly crystallized from the outside in, forming the ancient highlands that still cover much of the lunar surface today. And deep inside, the moon settled into the body it would remain for the next 4.5 billion years. There is a detail in all of this that scientists have found particularly fascinating, and it has to do with the moon's iron core. The Earth has a large iron core at its center. It makes up about half of the Earth's radius and accounts for a significant portion of its mass. The moon's iron core, by contrast, is small, very small. About 1 to 2% of the moon's total mass and roughly 420 miles across. This is exactly what you would expect if the moon formed mostly from the lighter outer layers of the colliding bodies, the mantles, rather than from their dense iron hearts. Theia's iron core, the theory goes, merged with what remained of the Earth's, sinking to the center of the reformed planet. The moon got the mantle. The Earth kept the metal. It is the kind of detail that makes the story feel real. Not a myth, not a speculation, but something that left fingerprints in the rocks. And those fingerprints were eventually found. Between July 1969 and December 1972, 12 human beings walked on the surface of the moon. They carried cameras and scientific instruments and, most valuably for the story we are telling tonight, sample bags. Over the course of 6 successful landing missions, the Apollo astronauts brought back 382 kilograms of lunar material, rocks and soil and core samples, packed carefully and carried home across the 250,000 miles of space between the moon and the Earth. Those samples have been studied and studied and studied again for more than 50 years. They have been examined with instruments that did not exist when they were collected. They have been analyzed by scientists who were not yet born when Neil Armstrong first pressed his boot into the lunar dust, and they have told a story that keeps getting richer and more detailed the more carefully anyone looks. One of the most important things those rocks revealed was their isotopic composition. This is a technical phrase for something that is, at its heart, quite simple. Different versions of the same element, called isotopes, occur in specific ratios in different places and under different conditions. By measuring the ratios of oxygen isotopes in lunar rocks and comparing them to Earth rocks, scientists can get a sense of where the material originally came from. What they found was striking. Material from different parts of the solar system has different isotopic signatures. The fact that the moon and the Earth are so similar in this way strongly suggests that they share a common origin, that the material the moon is made of was once part of the same world, or a world that formed in the same region of space under very similar conditions. This was one of the key pieces of evidence that elevated the giant impact hypothesis from an interesting idea to the dominant scientific explanation. But the rocks have continued to offer new details. A significant study published in 2020 examined chlorine isotopes in Apollo samples using more sensitive modern instruments than had been available before. Chlorine, lighter versions. What researchers found was that the Moon has a higher proportion of the heavier chlorine isotopes compared to Earth. This difference is thought to be a consequence of the impact itself. In the intense heat that followed, the lighter, more volatile forms of chlorine were more easily pulled away by Earth's gravity as the debris cloud began to separate, leaving the Moon slightly enriched in the heavier versions. It is a subtle difference, the kind of thing that takes decades of improving technology to detect. But it fits. It fits the model of a high-energy, high-heat impact, a cataclysm so intense that even the isotopic composition of a minor element like chlorine was sorted and separated by the forces involved. More recent computer simulations have also revised our understanding of how long the early Moon stayed molten. Earlier estimates suggested the magma ocean on the Moon's surface might have taken around 35 million years to fully crystallize. More recent modeling, published around 2020, suggests the process may have taken somewhere between 150 and 250 and 200 million years. The Moon stayed liquid for much longer than previously thought. It was a world of slow, ancient fire, cooling over timescales that make the entire history of human civilization look like the blink of an eye. And yet, for all that has been learned, questions remain. The precise size of Theia is still uncertain. Estimates range from something roughly the size of Mars to something closer to half the size of the present-day Earth. The exact angle and speed of the impact are still being refined by computer models, and one of the most persistent puzzles is the presence of water on the Moon. If the impact was as intensely hot as the models suggest, most water should have been driven off as vapor. And yet, in the permanently shadowed craters near the lunar poles, water ice has been detected. Where it came from, whether it was delivered later by comets and asteroids, or whether some survived the impact in ways not yet fully understood, is still a matter of active scientific discussion. There is something quietly wonderful about that. The story is not finished. The Moon has been there for 4.5 billion years, patient and still, and we are still learning how to read it. The Moon that emerged from all that ancient fire eventually settled into the relationship with Earth that we know now. And it is, when you think about it, a remarkably intimate relationship for two worlds to have. The Moon is about 1/4 the size of Earth, a ratio that is unusually large for a planet and its satellite. Most moons in the solar system are tiny compared to their parent planets. Our Moon is not. Some astronomers describe the Earth-Moon system as a kind of double planet, two worlds that formed together and have been keeping each other company ever since. One of the most important things the Moon does for us is something we almost never think about. It stabilizes the Earth's axial tilt. The Earth currently spins at an angle of about 23.5 degrees relative to its orbit around the Sun. This tilt is what gives us our seasons. The reason summers are warm and winters are cold, the reason the days are longer in June and shorter in December. Without the Moon's gravitational steadying influence, computer models suggest that Earth's axial tilt could wander dramatically over millions of years, swinging between near zero, which would mean almost no seasons, and very high angles, which would mean extreme climate swings. Some researchers have suggested that without the Moon, conditions on Earth might have been far less stable, and the long, steady periods of mild climate that allowed complex life to evolve and flourish might never have occurred. The Moon is also very slowly moving away from us. At a rate of about 3.8 centimeters per year, the Moon has been receding since the day it formed. In the distant past, it was much closer, perhaps 3 times closer when it first formed, glowing vast and red in the young Earth sky. As it has moved away, the gravitational interaction between the two bodies has gradually slowed the Earth's rotation. Days on the early Earth were much shorter, perhaps only a few hours long. The moon has been gently applying the brakes for billions of years. The 24-hour day we know is partly the moon's gift. We always see the same face of the moon. The result is that the moon always presents the same hemisphere to us, the far side, which is different in character from the near side, more heavily cratered, with fewer of the dark volcanic plains called Maria that give the familiar face its distinctive pattern, remained entirely unseen by human eyes. Until 1959, when a Soviet spacecraft sent back the first photographs. The Apollo astronauts also discovered that the moon is not geologically dead. Seismometers left on the surface detected moonquakes, small tremors in the lunar crust, caused by the tidal stresses of Earth's gravity pulling on the moon's interior, or by the temperature swings between the lunar day and night, which are extreme in the absence of any insulating atmosphere. The moon shudders, very gently, in response to the same gravitational pull that moves our oceans. It is a small, quiet sign of a relationship that is still active, still ongoing, even after 4.5 billion years. The moon's surface is heavily cratered because it has no atmosphere to burn up incoming asteroids and meteorites, and no plate tectonics to slowly erase the scars of old impacts over geological time. Those ancient craters are a record of the early solar system, preserved in the airless cold. The rocks brought back by the Apollo astronauts are generally between 3 and 4 billion years old. Holding one of those rocks, if you were ever lucky enough to do so, would be holding something that formed when the most complex life on Earth was a single cell drifting in a shallow sea. It is a long way from that to here. From a world of ancient fire and slow cooling to the pale, quiet presence outside your window tonight. And now, gently, we move to something closer. Something that connects that vast ancient story to the small, quiet world of your body, lying here in the dark. The moon has been with us for so long that it is woven into us in ways we are only beginning to understand. Human beings evolved under moonlight for almost the entire history of our species, and for the millions of years of evolutionary history before that, the moon was the only significant source of light after sunset. Our biology developed in a world where the amount of light available at night changed in a slow, regular cycle across 29.5 days. The lunar month. It perhaps should not surprise us then that researchers have begun to find traces of that ancient relationship in the rhythms of our sleep. A study published in the journal Science Advances in January 2021 looked at sleep patterns across a remarkably diverse range of people. The researchers from the University of Washington, Yale University, and the National University of Quilmes in Argentina studied indigenous communities in rural Argentina who had very limited access to artificial lighting, alongside college students in Seattle living in the fully electrified modern world. What they found across all of these groups was a consistent pattern. In the 3 to 5 days leading up to a full moon, people tended to go to bed later and to sleep for shorter periods overall. The effect was more pronounced in the communities with less artificial light, but it was present even in the Seattle students, muted but detectable beneath all the electric glow of a modern city. This suggests something worth sitting with. Other studies have added detail to this picture. During the days around the full moon, people appear to take slightly longer to fall asleep. Roughly 5 minutes on average, which sounds small but matters when sleep is already difficult. They sleep for a shorter total time, and, perhaps most meaningfully, they spend less time in the deepest stages of sleep. The stage researchers call slow wave sleep or deep sleep, the stage where the brain produces its slowest, most rhythmic waves, and where some of the most important restorative work of sleep takes place, appears to be reduced by around 30% in the days around a full moon. The mechanism that is most often proposed to explain this is moonlight itself. The full moon and the days leading up to it is when the moon is at its brightest in the early evening sky. That light, even when it comes through windows or reflects off walls and surfaces in indirect ways, is enough to subtly delay the body's production of melatonin. Melatonin is the hormone that signals to your body that it is night, that it is time to slow down, that sleep is approaching. When light, even dim light, reaches the eye in the evening, the brain's internal clock reads it as a signal to stay a little more alert. The full moon has been sending that signal to sleeping creatures for as long as there have been sleeping creatures. There is also some interesting research suggesting that this effect may differ between men and women. A 2021 study from Uppsala University in Sweden found that men showed more disrupted sleep during the waxing phase of the moon, when the illuminated portion of the lunar surface is growing toward full, while women in the study were less affected. The researchers speculated this might relate to differences in sensitivity to ambient light, or to fluctuations in hormones like testosterone and cortisol that may themselves track lunar rhythms in ways not yet fully mapped. This area of research is still young, still finding its footing, but it points toward a picture of the human body as something more deeply entangled with the moon's cycles than we generally acknowledge. The sleeping brain is, in its own way, a world of rhythms and cycles. When you close your eyes tonight and begin to drift, your brain will move through a series of distinct stages, each characterized by its own electrical signature. In the early moments of sleep, the fast, busy waves of wakefulness begin to slow. Alpha waves, which hum along at somewhere between 8 and 13 cycles per second when you are relaxed but awake, give way to the slower theta waves of early sleep, moving at 4 to 7 cycles per second. The world begins to feel distant. Sounds lose their edges. The thoughts that were so insistent an hour ago become looser, less coherent. As sleep deepens, the brain's activity slows further still. Brief bursts of faster activity, called sleep spindles, flicker through the theta background like small quiet fireworks, helping to consolidate the memories of the day. Then, deeper again, the slow waves emerge. Delta waves, moving at less than 4 cycles per second. Great slow swells of electrical activity rolling across the brain like tides. The brain moves through these stages and cycles across the night, dipping down into deep, slow-wave sleep and then rising back up through lighter stages before entering the rapid eye movement phase, where dreams are most vivid and the brain's activity looks, on a monitor, almost like wakefulness. Then the cycle begins again. 4 or 5 times across a full night's sleep, the brain makes this slow, rhythmic journey. It is a profound thing when you consider it in the context of everything we have been talking about tonight. The same moon that was born from fire, that has been holding the Earth's tilt steady for billions of years, that pulled the oceans back and forth across the face of the planet long before there were coastlines to shape. That same moon is, in a small and subtle way, still reaching into the bodies of sleeping creatures, still sending its light through the dark. Still, after all this time, part of the rhythm. There is something you can do with this knowledge if sleep has been difficult lately. Not a dramatic solution, nothing that requires effort or willpower, just an awareness. The brain cannot be forced into sleep any more than you can force a tide. But by offering a steady, slow rhythm, something the brain can orient toward, the way a ship orients toward a lighthouse. A gentle guide in the dark. The brain has a natural tendency to synchronize with rhythmic patterns in its environment. It is called entrainment, and it is not a trick or a technique. It is simply something the brain does, has always done. the same way it once synchronized with the rhythms of the night sky outside a cave or a shelter, or a place in the open grass where a sleeping creature felt safe enough to close its eyes. When the sounds around you are slow and steady, the brain takes that as information, as a cue, as permission to slow down too. You do not need to try to listen. You do not need to concentrate on the frequencies or understand them. You only need to be here, in the dark, letting the sounds arrive the way the moonlight arrives, without effort, without intention, simply present. There is a quality to the moon tonight, wherever it is in its cycle, that is worth noticing before you drift too far from waking. It is the same moon that hung over every human being who has ever existed, over every person who ever lay awake in the dark, wondering about something, worrying about something, hoping for something, over every child who ever fell asleep being told a story about the stars, over every sailor who ever used its light to find the way home. The ancient Mesopotamians tracked its cycles and built calendars from them. The Greeks gave it a goddess, Selene, who drove her silver chariot across the night sky. In Chinese mythology, Chang'e lives on the moon in a palace of cold jade, accompanied by a rabbit and the slow turning of the seasons. The Inca called their moon goddess Mamaquilla and believed she wept silver tears. In Japan, Tsukuyomi was the god of the moon, born from the right eye of the creator deity Izanagi, made from a mirror of white copper held up to the night. Every culture that has ever looked up has made something of it, has reached toward it with story and symbol and longing, because it is there every month, reliable and changing and the same all at once, because it is beautiful in a way that does not require explanation, because something in us, something very old, responds to it. And now we know something those ancient storytellers did not, that the moon's gravity has been steadying our planet's tilt for 4.5 billion years, creating the conditions for everything that ever lived here, including us, including you, lying here now in the dark. The moon is not separate from the story of life on Earth. It is part of it, has always been part of it. The stability it provides, the tides it pulls, the light it lends to the dark hours, all of it has been woven into the fabric of living things for as long as living things have existed. And somewhere in your body, in the faint rhythms of your sleep, in the ancient chemistry of melatonin and cortisol, and the slow oscillation of your brain's electrical tides, the moon is still, very quietly, present. That is not a metaphor. It is simply what the research is beginning to show us. That the connection between the moon and the sleeping human body is real, however subtle, however easy to drown out with the electric light of modern life. That we are not as separate from the sky as we sometimes feel. That the ancient relationship between a sleeping creature and the moon overhead is still, in some form, alive. If today was hard, if whatever you were carrying felt heavy, if the thoughts came fast and the quiet came slow, then this is for you especially. The moon has been watching over sleeping things for longer than there have been sleeping things to watch over. Whatever you are worried about, it has seen worry before. Whatever you are carrying, it has watched others carry things just as heavy and set them down and rest. And it is still there, patient, unhurried, distant and close all at once. Your brain is already beginning its own slow turning. Already the faster waves are softening at the edges. Already the body is doing what it knows how to do, what it has known how to do for the entire history of your kind. The sounds around you will stay steady. The dark will stay. The moon, wherever it is tonight, is doing what it has always done. You don't need to do anything at all. And so we leave it there, somewhere between the ancient fire that made the moon and the quiet dark where you are now. Somewhere between a collision 4.5 billion years ago and this moment, this particular breath, this particular stillness. The story is very old. You are in it. Somewhere behind you, the day is already distant. The moon is where it has always been. The deep, slow waves are coming. Drift now, if you're ready. Sleep well. It is worth pausing for a moment on that word, accretion, before we move on. Because it describes something that has a kind of quiet poetry to it when you hold it still and look at it. The universe does not build things all at once. It builds them slowly, grain by grain, collision by collision, each small addition almost undetectable on its own, the change only becoming visible across enormous stretches of time. A pebble is just a pebble. But given enough pebbles and enough time and the patient, unhurried work of gravity, you get a world. There is something almost restful in that idea, that the largest things are built from the smallest accumulations, that nothing has to happen all at once. The region of the early solar system where Earth was forming is sometimes called the habitable zone, though at that stage there was nothing remotely habitable about it. It was simply the band of distance from the young sun, where temperatures were neither so hot that all volatile materials were driven away, nor so cold that everything froze before it could gather. A middle place. A place where the right kinds of things could come together in the right proportions. Theia was forming in this same region. Some researchers believe it may have been orbiting at one of the gravitational sweet spots in the Earth's own orbit, points called Lagrange, points where a smaller body can orbit stably in relation to a larger one. If that is true, it would have been there for a very long time, growing quietly alongside the proto-Earth, before the slow drift of gravitational perturbations eventually nudged it onto a different path. A companion, in a sense, before it became something else entirely. Two worlds, growing up side by side in the same quiet neighborhood of space for millions of years before the forces that govern all things brought them together. We do not know exactly how long Theia took to reach its final size. Estimates suggest it may have been comparable in mass to Mars within a few tens of millions of years after the solar system formed. It would have had its own geological activity, its own internal heat from the energy of its own accretion, possibly its own early crust, forming and reforming on a surface that was slowly cooling. A world with its own story, however brief, however unwitnessed. And then that story ended, and a new one began. The simulations that scientists run to model the giant impact are among the most computationally demanding in planetary science. They require tracking hundreds of thousands of individual particles, each representing a volume of rock or metal or vapor, each interacting gravitationally with every other, across a timescale of hours and days and weeks following the initial impact. The results of these simulations have been refined many times over the past few decades as computing power has grown and the physical models have become more sophisticated. One of the most striking things the simulations show is how quickly the moon-forming disk assembled itself into something coherent. Within hours of the impact, the debris cloud already had a rough structure. Within days, the largest fragments were beginning to dominate, sweeping up smaller material through their own gravitational pull. Within a year, the simulations suggest most of the material that would eventually become the moon was already in a roughly disc-shaped structure around the Earth. The inner edges of the disk held back by tidal forces from the Earth itself, the outer edges slowly condensing toward what would become the lunar body. A year. From the end of two worlds to the beginning of a third in something like a year. Some of the more recent simulations, particularly a family of models developed around 2012 by researchers including Sarah Stewart at the University of California, Davis and Matija Tuk at the SETI Institute, suggest that the impact may have been even more energetic than earlier models assumed. These high-energy models proposed that the collision was nearly head-on rather than oblique, and that it involved an Earth spinning very rapidly at the time of impact, perhaps completing a full rotation in just 2 to 3 hours. In this scenario, the impact would have been even more catastrophic, effectively vaporizing and thoroughly mixing the outer layers of both bodies before the debris settled into a disk. This would help explain the striking similarity in isotopic composition between Earth rocks and lunar rocks, since a more thorough mixing would have erased the chemical differences between Theia and the proto-Earth more completely. The debate between these models is still ongoing. It is one of the genuinely open questions in planetary science, a field where the evidence is extraordinary, but the distances and timescales involved mean that certainty is always approached slowly, from a great way off. What is not in serious dispute is the general outline. A large body. A collision. A disk. A moon. The details are still being refined, the way a portrait is refined when the painter steps back and looks at it again in better light. But the subject of the portrait is clear. Among the Apollo samples, there is a particular rock that has become something of a symbol for lunar science. It was collected during the Apollo 15 mission in August 1971 near the base of the Apennine Mountains on the Moon's surface by astronaut David Scott. It is a piece of anorthosite, a pale, crystalline rock made largely of a mineral called plagioclase feldspar. The sample is 4 billion and 15 million years old, give or take about 20 million years. It was given a name, as the most significant Apollo samples were. Scientists call it the Genesis Rock. The reason for the name is what it represents. Anorthosite of this kind is thought to be among the oldest material on the Moon's surface, a remnant of the original crust that formed as the magma ocean slowly cooled and the lighter minerals floated to the top and solidified. Holding the Genesis Rock in your mind tonight, this small pale piece of ancient crystallized ocean is a way of touching the very beginning of the Moon's solid history. The moment when fire became stone. The Genesis Rock is kept in a nitrogen-filled cabinet at the Johnson Space Center in Houston, Texas, to prevent it from being contaminated by Earth's atmosphere. It has been analyzed dozens of times over the decades since it was brought home. Each new analysis has added something to the picture. The precision of modern mass spectrometry, instruments that can measure the ratios of different isotopes with extraordinary accuracy, has allowed scientists to date it with a confidence that would have seemed almost impossible to the geologists of the Apollo era. There are other samples that have told equally important stories. Tiny glass beads found in the lunar soil, formed when micrometeorite impacts melted the surface rock and flung it briefly into the airless sky, where it cooled and solidified into spheres before falling back to the ground. These beads have been found to contain small amounts of water trapped inside their glassy interiors. The water is ancient. Some of it may date back to the very early Moon, preserved inside the glass like a message in a sealed bottle. Some of it may have been delivered later by the steady rain of comets and asteroids that continued to bombard the inner solar system long after the planets formed. The distinction matters because it speaks to one of the most interesting questions in the science of the Moon's origin. If the impact that created the Moon was as intensely hot as the models suggest, most volatile compounds, including water, should have been driven off as vapor and lost to space. And yet water is there, in the glass beads, in the polar ice deposits, in trace amounts in some of the minerals. Either some water survived the impact in ways the models do not yet fully capture, or it was delivered afterward, or both. The answer, when it comes, will add another layer of detail to a story that has been 4.5 billion years in the making. The Japanese lunar orbiter Kaguya, which operated from 2007 to 2009, added further evidence by mapping the distribution of minerals across the lunar surface with greater precision than had previously been possible. It confirmed the presence of anorthosite highlands across large areas of the far side, consistent with the magma ocean theory. India's Chandrayaan 1 mission, also operating in 2008 and 2009, carried an instrument called the Moon Mineralogy Mapper, built by NASA, which detected the spectral signature of water molecules and hydroxyl groups in the lunar soil at high latitudes. Not liquid water, nothing like that, but the chemical signature of water, bound into the surface minerals, spread across a wider area than the polar ice deposits alone. China's Chang'e missions have continued this work into the present decade. The samples came from a geologically younger region than the Apollo landing sites, a volcanic plain called Mons Rumke, and early analysis suggested they were formed around 1.9 billion years ago. This was younger than any previously returned sample, and it raised new questions about how long the moon remained geologically active, how long volcanic eruptions continued to resurface parts of its interior. The moon's story, it seems, did not end with the cooling of the magma ocean. It continued, quietly and slowly, for billions of years more. The tides that the moon pulls across the Earth's oceans are one of the most visible expressions of that ongoing gravitational relationship. Twice a day, in most coastal locations, the ocean rises and falls in response to the moon's pull. The effect is largest at new moon and full moon, when the sun and moon are aligned and their gravitational influences combine into what are called spring tides, not because they happen in spring, but because of an older meaning of the word related to the idea of water springing upward. At quarter moon, when the sun and moon are at right angles to each other from Earth's perspective, the tides are smaller, called neap tides, a word whose origins are equally ancient and obscure. The tidal range, the difference between high tide and low tide, varies enormously depending on the shape of the coastline and the geometry of the ocean basin. In the open ocean, the tidal range is only about 0.5 meter, but in certain places where the shape of the land concentrates and amplifies the tidal flow, the range can be extraordinary. The Bay of Fundy, on the Atlantic coast of Canada, has the highest tidal range in the world, with water levels changing by up to 16 meters between high and low tide. 16 meters is the height of a 5-story building, rising and falling twice a day, every day, pulled by the same moon that hangs quietly in the sky tonight. Those tides have been shaping the Earth's coastlines and the life that lives along them for as long as there have been coastlines. The intertidal zone, the strip of shore that is submerged at high tide and exposed at low tide, is one of the most biologically productive environments on the planet. It is a place of constant change and extraordinary adaptation. The creatures that live there, barnacles and limpets and sea anemones and the small fish that shelter in rock pools, have evolved their entire biology around the rhythm of the moon's pull. Their feeding times, their reproductive cycles, their tolerance for exposure and submersion, all of it shaped by a schedule written in the sky. The grunion, a small silver fish that lives off the coast of California, takes this relationship to a remarkable extreme. On the 3 or 4 nights following the highest tides of the year, which occur at new moon and full moon in spring and summer, grunion come ashore in enormous numbers to spawn. The females ride the waves onto the beach, dig themselves into the wet sand and deposit their eggs. The males fertilize them. Then the fish ride the receding waves back into the ocean. leaving the eggs buried in the sand above the tide line, where they will incubate safely until the next set of high tides 2 weeks later reaches them and triggers the eggs to hatch. The hatchlings emerge directly into the wave and are carried into the sea. The Grunions' entire reproductive strategy depends on reading the moon's tidal calendar with precision. It is a strategy that has been working for a very long time. And it is a reminder that the moon's influence on living things is not limited to the vague and subtle rhythms of human sleep. For many species, it is immediate and absolute, and the entire architecture of their lives is built around it. Coral reefs, which are among the most biologically diverse ecosystems on Earth, also synchronize their reproduction to the moon. Many coral species release their eggs and sperm simultaneously in a mass spawning event that happens once a year, typically in the nights following the full moon in late spring or early summer, depending on the location. The synchronization is thought to be triggered by a combination of water temperature, the length of the day, and the intensity of moonlight. The result is an event of extraordinary scale, a blizzard of tiny reproductive packages rising through the water column across hundreds of kilometers of reef, all at the same time, maximizing the chances that eggs and sperm from different coral colonies will meet and fertilize. The Great Barrier Reef's annual spawning event has been described by divers who have witnessed it as one of the most astonishing natural experiences available to a human being. An ocean full of rising life, all of it timed to the moon. There is a researcher named Christian Kajorken who works at the Center for Chronobiology at the University of Basel in Switzerland, whose work on the moon and sleep has been quietly influential. In 2013, he and his colleagues published a study that was, in its own way, a small piece of scientific detective work. The study had not originally been designed to investigate the moon at all. Kajorken's team had been collecting sleep data from volunteers in a controlled laboratory setting for years, monitoring their brain activity through the night, their melatonin levels, their sleep duration. The volunteers slept in rooms without windows, with no way of knowing what phase the moon was in. When Kajorken went back through the data years later, he noticed something. In the days around the full moon, the volunteers had taken longer to fall asleep, slept for shorter periods overall, and showed reduced slow-wave activity in their brain recordings. The effect was there even though the participants could not see the moon, even though they had no way of knowing what phase it was in, even though the laboratory conditions were carefully controlled to exclude external light. The implication was intriguing. Whatever was driving the effect did not appear to be simply the light of the full moon coming through a window. Something else might be involved, perhaps an internal biological clock, a circulunar rhythm, some ancient timing mechanism that had been entrained by millions of years of evolution under lunar light and had not yet let go entirely, even in the controlled darkness of a sleep laboratory. Kajorken was cautious in how he presented this finding. The sample size was not large. The effect, though statistically significant, was subtle. It needed replication, and it has been followed by the later, larger studies that found similar patterns. The University of Washington study across communities in Argentina and urban students in Seattle. The Uppsala University work on differences between men and women. The picture that is emerging is not one of dramatic lunar control over human biology. It is something quieter than that, a faint resonance, an old frequency that the body has not quite forgotten. The hormone melatonin, which sits at the center of this story, is produced by a tiny structure deep inside the brain called the pineal gland. It is sometimes called the third eye, not because it can see in any literal sense, but because in some ancient vertebrates it does respond directly to light filtering through the skull. In humans, it receives information about light and dark indirectly, via a pathway from the eyes through the brain's internal clock, a small cluster of neurons in the hypothalamus called the suprachiasmatic nucleus. The suprachiasmatic nucleus is the master timekeeper of the body. It coordinates the rhythms of nearly every organ and system, telling them when to ramp up their activity and when to slow down, all based on the light information it receives from the eyes. In the natural world before artificial light, the information this clock received was simple and consistent. Bright sunlight in the day, darkness at night, broken only by firelight or moonlight. The melatonin signal was clear. As the sky darkened, melatonin production rose, peaking in the middle of the night and fading as dawn approached. The body knew exactly where it was in the cycle of day and night and acted accordingly. The full moon introduced a small but meaningful variation into that signal. A few extra lumens of reflected sunlight, coming from above, changing across the month in a slow, predictable rhythm. Enough, over millions of years, to leave its mark on the biology of creatures that slept under open skies. Enough, it seems, to still be faintly present in the sleep architecture of a person lying in a modern bedroom with blackout curtains and a phone charging on the nightstand. If you have ever found yourself lying awake on a night when the moon is full, unable to settle, your mind moving in that particular restless way that resists sleep without quite engaging with any single thought, you may have been feeling the edge of something very old. Not the moon's fault exactly. Not a problem to be solved. Just the body doing what it has always done. Responding in its ancient way to a signal that has been part of its environment for longer than the species has existed. The sounds accompanying this video are calibrated to the slower end of the brain's natural frequency range. The delta range, below 4 cycles per second, that territory of deep, slow, restorative sleep that the research suggests is gently compressed in the days around a full moon. The intention is simply to offer the brain a direction. A soft suggestion, the way the smell of rain suggests shelter, or the feeling of a heavy blanket suggests warmth. The brain does the rest. It always does the rest. It knows the way.